Hello, everybody. Thank you so much for joining us. We are so excited to get started. We have a really exciting presentation for you today. As folks kind of settle into the webinar room and get comfortable, I'd love to direct you down to the bottom of your Zoom window. Right at the bottom of your Zoom window, under where you can see the video, you'll see what looks like a little chat bubble. Now, if you click that, that will open our chat box, the conversation area. That's how we'll be accepting questions, comments, etc. So we don't have a Q&A function, anything like that. So if you have a question, don't raise your hand, go ahead and just pop that right into the chat. When you pop a question into the chat or a guess, a suggestion, today's presentation is a little interactive, so you'll have the opportunity to do that. Do make sure that that little blue button, it says to, and then it may be set right now to hosts and panelists. Make sure you click that blue button and change it to everyone. That way, everybody can see your question, your comment, your suggestion. There's two reasons why we ask you to do this. Number one reason, because it encourages community. This is how we support one another. We show other educators that we are also wondering that thing. We have this idea. It makes it okay for other people to share their thoughts and ideas. So just like you want your kiddos to raise their hand in class, feel free to be the one to share that comment in the chat. The second reason we ask you to set that button to everyone is because we will be answering your questions live, and we don't want to look like we're talking to ourselves. So please make sure that your question is there for everyone to see so that when we answer that question, they understand what we are talking about. In an effort to practice those skills, go ahead and navigate down to that chat bubble and let me know how much snow have you gotten this week, or how much snow did you get over the weekend, and what is the temperature where you are? So here in Oregon, at least where I've been, I don't think we got any snow, but it did get down to 30, I think just below freezing, which for,
28. Yeah. Ooh,
yeah.
18 inches of snow. Oh, wow.
Oh, Janine,
Ooh.
12 inches for Kurt, and it is,
Oh, 14. Oh, no, thank you.
Zero.
wow,
Oof.
18, yeah,
Oh, goodness.
18
Stay
inches.
warm, everyone.
Wow, San Antonio.
Yeah.
Wow. 9.5 inches and 11 degrees for Judith, 8 to 10 inches and 24 degrees for Joshua. Los Angeles, high of 71. All right. In Philadelphia. Okay.
Yeah. Crazy.
Yeah, that's amazing.
And
Well,
some crazy weather.
yeah, I hope everyone's staying nice and warm. Wow, wow, wow. All right, my friends, we are about 2 minutes. Ooh, okay, just quick. Jen Clancy shares that it is -4 degrees in upstate New
Oh.
No,
York.
thank you.
Ooh, yeah.
When the snow squeaks when you walk on it.
Yeah. I remember that from Colorado. All right, my friends, let's hop into some quick housekeeping items, and then I will pass you off to today's presenters. So as always, you will get a recording of today's webinar. It usually takes us about 3 to 5 business days to get that edited, but as soon as it's ready to go, I'm going to drop it in two places, one on our YouTube channel and two on our website. As soon as it's ready, I'm also going to email it to you. So keep an eye out for an email from us. It's going to have the recording of today's webinar. In that email, you will also gain access to our resources folder. The resources folder has a certificate of attendance and all kinds of goodies for you. I'm going to drop the link to that into the public chat here in just a second, so keep an eye out for that. As I mentioned before, we want to answer your questions during today's presentation. So if you have a question, comment, suggestion, anything, go ahead and drop that into the chat and we will address it as it pops up. But if we happen to not get to your question, we do want to help out, or if you think of one later. So should that happen, please reach out to us at info@vernier.com. Stick around till the end because we are doing a giveaway at the end of today's presentation. So anyone who is live in the webinar at that time will be entered to win. With that being said, I'll go ahead and pass you off to today's presenters, and thank you again for joining.
Hi, everyone. I'm Melissa, and I actually have my co-host here
I'm Colleen.
in the room with me. I am one of the chemists here at Vernier, and as such, we kind of do these teacher trainings and write labs and develop products all for you. So we're going to be demoing a few actually experiments today, and I'll let Colleen introduce herself.
I'm Colleen. I'm one of the biology and environmental science specialists here today. So I'm here to give the biological side of these experiments and show how chemistry and biology, we get along.
Yeah, we do. We do get along. All right, so let's jump right in. Today we are going to be doing all kinds of stuff with comfort foods. So it's especially cold. Now, we didn't realize how cold it would be when we set up this webinar and the topic for it. But we're going to be looking at different kinds of comfort foods and the science behind them. So we're going to be looking at hot chocolate with a temperature probe, milk and different kinds of cooking with milk and its pH. And then we are going to look at vegetables with our spectrometer. So here we go. Why does hot chocolate cool so differently based on the mug that you have? So we are about to walk outside with some hot chocolate. We want to stay warm, and we have two different kinds of mugs. We have here my very fun periodic table of elements, double-walled, kind of tall mug here. And then I have a typical ceramic mug. So everyone out there, and I'm going to let Dylan speak. Dylan's going to be our student today, but please jump in the chat and give your suggestions. Which mug do you think will keep the heat in better between these two of our hot chocolate? Which would you rather take out with you in the, my goodness, -4 degrees in New York?
Man, all right, you all are my study group, so please help a girl out. Let me know in the chat which you think. While you're dropping that in, I'll let you know my off the top of my head guess would be the mug. I mean, that's what we put our morning coffee in. I know that ceramic, it warms up in the microwave, so I assume it's a good conductor of heat. And I'm looking in the chat. I've got a vote for the mug. Let's see, I think 2 or 3 mug votes. I think I've got, ooh, the group is leaning towards the periodic
Oh,
table cup.
yeah. Ooh, it's almost like 50-50.
Yeah.
Yeah.
Yeah, pretty cool. All right, we'll keep it longer warmer. All right, awesome. Well, we're going to test this today, so we're all going to find out. I have some hot chocolate over here heating on my hot plate, and I have 2 temperature probes. So first we need to connect our temperature probes. So I'm going to turn them on by pushing this teal button right here. And I'm going to use the web-based version of our software, of our graphical analysis software. And to go there, I just open a new Chrome web browser and I start typing in graphicalanalysis.app. Enter. And I have graphical analysis right here. Now I am going to click on sensor data collection because that's the data, that's what I want to do. I want to take data from the temperature probes. So I will click on that. And because this is the web-based version, I have to tell it to go look for the Bluetooth signal from the temperature probes. If I had them connected via USB, which I could do from the top of the sensor right here, I could plug in the USB cable and connect it. I would still have to do this step because the Chrome web browser doesn't have access to my USB ports. All right, so I'm going to say wireless. And now in order to find my temperature probe, I look on the back of my temperature probe and there's a barcode right here. And it's really hard to see in the camera, but there's a number above the barcode and it ends in K4. So I just need to find temp and K4 at the end. So where is it?
I just saw it in there.
Temp K4.
Come back up.
Oh, there it is. Pair.
We have
All right.
too many sensors in the building.
Yeah, we have a lot of sensors in the building. And then now that it's connected, it is flashing green. You can kind of see that. And now I can absolutely, we get this question all the time. Can I connect more than one sensor at a time? I absolutely can. I go in here and do the same process, and this one ends in 8.5. That's right here. All right, and I'm going to say done. And so now everything's all connected and set up. I am going to want to take data for longer than 3 minutes. So I'm going to go ahead and extend my data collection just a little bit. I could change it to minutes, but I don't want to do that. At this point, I'm going to put 360. We can always stop it early and say done. I also want to make these little meters down here a little bit bigger because they're very tiny right now. So I'm going to come in and open the meters. Okay, and now I'm all set for data collection. I just got to get my hot chocolate. And what's important here is that I want the hot chocolate to be pretty close to the same temperature when I pour it in each of the mugs and start doing data collection, because we care about the cooling curve mostly, but I'm going to go ahead and capture all of it. So first I'm going to turn off my hot plate. I'm not going to need it anymore. Use my hot pad. And this is just actually powdered hot chocolate. You can use kind of any hot chocolate. You can get fancy hot chocolate.
I mean, this is Trader Joe's organic.
Oh, right, it is Trader Joe's.
Trader Joe's organic hot chocolate we are using.
That's very fancy. All right, and I'm going to do 200 milliliters of each, and I'm just going to pour into these beakers first so that I can get them into my mugs at the same time. Okay, and I want to have the same amount in each. All right, and now I'm going to put my temperature probes in my mugs, and I'm going to press collect. And then I am going to use my hot pads, and I'm going to pour and hopefully get something kind of close.
Ooh.
There we go. All right, hey, not too bad. So some things that you can talk about with your students here while we wait for this really exciting temperature curve to come in. So not only having them kind of guess which one they think will hold the temperature better, but what evidence would you use to like help you decide? What things are important to control for? Like, why did I spend so much time making sure I had the same volume or that they were approximately like treated exactly the same before I pulled it in? So all those types of things would be really helpful to get them to start thinking about which one would be better. Not only everyone kind of brought up the materials, and I pretty much prompted that with like how I described the mug, but you could also just like give them a table full of mugs and say which one and go figure it out. This is, ooh, exciting. We're getting some data coming in.
It changed really quickly.
Yeah, it's pretty quick. The only reason I changed the time in it is so I just have a lot of runway because I hate when my data is like cut off too soon. So let's see, we can, what do we want to talk all about the connecting? So let's go through GAs. You know, should we walk through graphical analysis? Definitely put questions in the chat if you all have any questions. Which color is, excellent question.
Kimberly, you gave us a great leading question.
So there's a couple ways I can determine which color trace is which mug. I click on the little, it's designed to be a little temperature probe icon here in the lower right corner. I click on that and I can see that K4, I can look at some details of it, but it still doesn't tell me which one is which. However, I have this little button right here that says identify. And if I click on it, one of them will go faster than the other. Ooh, does it work well during data collection? I don't think it does.
Should.
Identify. Well, we'll have to check it again. Well, it should be. I also tend to think it's in the order. I don't think I've ever seen it be backwards. That K4 is the first one that's connected, so it's temp 1. And 8.5 is the second probe that's connected, so it's temp 2. And what I actually like to do is you can change what these things say. Yes, you can. That's exactly right.
You can't rename the probes, but you can rename the runs or the data sets in here.
I can rename temperature 1 and temperature 2. I go in here to column options.
Oh, to the column options.
Yeah. So I can't rename them in like the Bluetooth name of it, if that was what it was. But I can come in here and say temp 1 is, I forgot now which one was K4. Yeah. And this one was the periodic table cup. And I can go in here to temp 2, column options, and I can say this one was the ceramic mug. And I can even get a graph legend by clicking down. In the lower left-hand corner is all the graph options. So lots of things about statistics, how you want the graph to look, like the max and min and zooming in and zooming out are all in this lower left-hand corner. If I click on that, I can turn on the graph legend. And it's itty bitty tiny, but I can adjust it and I can even move it around. I can click along the graph. I can double click to zoom in. I can highlight a section of the graph and a lot of graph options come up as I've highlighted it. So for this, I am going to want to look at, well, why don't you all tell me, how am I going to determine which one holds heat better? The width of the mug opening may be a factor. Ooh, that absolutely may be a factor. But how am I going to determine which one of these held the heat better? Based on this, the slope, the delta T. Yeah, absolutely. We can do both of those things.
Yes.
And so I'm going to go ahead and stop data collection, and I'm going to select the region of the graph that I think looks the most linear. And I'm going to do view statistics to do a delta T. So the purple one, which is my periodic table mug, changed 7 degrees Celsius. And the purple and blue is very hard to see. Does anyone else think that? I'm going to go ahead and change the color of purple and blue and make it a little easier to differentiate those colors. And I do that the same way by clicking on this y-axis label and clicking on the color. In Vernier land, I always like to say, if you want to change something, click on it. So let's pick orange and blue.
Much better.
And now I can see, let me do statistics again so it refreshes. And now I can see clearly the orange one here, that's the little line on the side, changed 7 degrees Celsius, whereas the blue one, the ceramic mug, changed 11 degrees Celsius. So the ceramic mug actually let go of more heat. compared to the periodic table, the double-walled mug. So it was everyone had like a 50-50 and it's been really kind of exciting to hear. Dylan, as our resident student, what do you think of that? What do you think of that? Give us some theories around why this one would actually hold on to the heat better than this one.
Yeah, I mean, as we kind of mentioned before, that's surprising to me because, you think of what holds in hot liquid, it's a mug. I did see a comment in the chat, and I'm sorry, I don't remember who it was, but please, if this was you, jump in and take credit. Somebody suggested that it might have to do with the air between the two sides of the cup. Let's see. Who was that? And folks, if there are other ideas that you want to drop out there, come on in and let me know. So, let's see. Charles guesses perhaps the airspace head in the taller tumbler acts as a thermocline, which is a much better way to say what I
Well,
just.
no, actually, I think what Charles is thinking of is looking at the actual height of the periodic mug is
Mm.
actually taller than the ceramic mug. So you have, in a way, kind of more of an air gap holding in some of that heat, which could be having an effect as well. So ideally, this could be a source of error for us of, some differences in our experimental setup.
Yeah, so how would I test that theory?
I would get a mug that's the same size, same height.
You could get a double-walled mug that was the same height. Someone talked about the openings on the top. You could close the tops.
Mm-hmm.
Um,
Will in the chat suggests get out your saw.
yes. Yes, that's stay tuned for the next webinar where our physics team will be looking at that. Um, so see, this is just something like really interesting that you can kind of bring to your students and ask them how they would do it, different materials, different designs, how all that affects how the energy leaves the system. You can even talk to them about the thermal energy leaving the cup onto the surroundings. You can do some Q equals MC delta T equations. I wouldn't recommend doing it in like a quantitative way, but you can talk about the mass, you can talk about the heat capacity, and you can talk about the delta T. We did also do, I know we were all talking, but I did a slope on the runs there just to verify that like the starting point didn't affect my slope. So we got lots of good ideas around all of that.
And this actually, I really love this idea because it's a way to kind of introduce the concept to your students and get them interested of why something like this matters in the real world. Because that's where we're looking at trying to make those real world connections and showing that, these are things that, engineers and people consider when they're designing these and trying to figure out um, why it's better one way or the other.
Yeah. Absolutely. All right. Well, let's move on because we have a couple other experiments to get through. And so the next one that I want to go into is talking about different kinds of milk and how they interact with acids. And a common one, at least that I run into, is when I put milk in my coffee in the morning and it curdles and it looks like this. And I absolutely hate that because I'm a texture eater and I don't like that. That texture in there. But it's also a really important phenomenon because it's how you make like buttermilk and cheese. It's a fundamental part of making cheese. So why would some milks do this and others don't? Could I pick a different milk for my coffee in the morning that wouldn't do this? Can I make buttermilk with every different kind of milk? So these are kind of your intro questions for students that might help them relate to what we're talking about. Today I have whole milk and oat milk over here. So other than the color, if you can see the subtle difference in color, what are the differences between whole milk, whole dairy milk, and oat milk?
Stephen has a good question. Would fat content play a role? We think it might. That is why, if we had more time, I was going to buy some multiple types of milk that we could compare, but due to time shortage, I went with just whole milk. Also, because whole milk is really good for making hot chocolate, which we did earlier.
We did. We already drank it.
Yeah, sorry. And to be able to compare that to, and I would like to try different types of plant-based milks as well, or
Yeah.
mulks.
Yeah. All kinds of variables we could test here. But today we're just, as Colleen said, for the sake of time, we're going to look at whole dairy milk and oat milk. So we think fat content might be a difference between the two. What else? Protein, different protein mix, right? Dylan, what do you think? You're our resident student today.
Yes, well, I've been learning in the chat, and I want to kind of echo what Aline said, which is that it will have something to do with the different protein mixes. I'm thinking that specifically in, I think you said whole milk and oat milk, am I right? I think that there's something about the way that the proteins in animal milk are structured that the acid is going to impact them more, or they're something a little grittier going on there.
Okay.
I'm excited to find out.
All right, me too. Yeah, I'm gonna kind of clean off my stir bar here a little bit. First, let's do a couple observations. Whole milk, if I kind of, oh, you're not gonna be able to see it very well, but it like clings to the glass really well, and it never really looks completely homogeneous, right? Like we always talk about how milk is actually not a homogeneous mixture because of the proteins and the other things we talk about that are floating in it. Oat milk has a little bit different, it's a little less watery, so maybe it looks a little more homogeneous of a solution. So just having your students note that, take a look at it before we do any kinds of measurements. We are talking about adding it to lemon juice in the case of making cheese, or to coffee. Those things are acids. So we're going to test the pH ahead of time, and then we are gonna add some acid and see what happens, and then test the pH again. So I am actually just going to close this and open a new tab because I find that to be the fastest when switching between sensors. And I have right here my pH probe. So I'm going to push the teal button to get the flashy blue light, which means it's broadcasting, and click wireless.
A question of from heat capacity difference, can you estimate the fat content? I'm not sure on
Of the hot chocolate one?
with the milk. With the milk.
Oh, you would want to do it at different temperatures, right? You'd want to do a heat capacity analysis. And like do a calibration curve is how I would see that going. I haven't done it myself. It's a great idea.
So Mark has a good question. Can a probe transmit to more than one computer?
Why don't you take that one?
So that's a great question, Mark. So a probe can only connect to one device at a time. But with the pro features in graphical analysis, we could actually stream this data over the internet and everybody could have a copy of it. which Melissa's actually activating the GA Pro features right now.
Yeah, so when we did the temperature data, we did that with the free version of graphical analysis. There's some niceties in a paid version of graphical analysis. We call it Graphical Analysis Pro for this next experiment with pH and telling it what milk is what. So I want to enable my Graphical Analysis Pro. And to do that, I type in a license key, and you all have access to this license key. It will give you Graphical Analysis Pro for the next couple of weeks. And it's in the slide deck, and I will put it here in the chat as well. So feel free to take advantage of that. And then now I press submit. And so now I'll have Graphical Analysis Pro, and I go into my sensor data collection, and it remembers that I connected to the pH probe. And it has this annoying red bar at the bottom, so I just close that. Okay, and so for this kind of data collection, because I want to measure the pH before and after I add acid to these various samples, that's not time-based data. That is me wanting to tell it the variable that I am testing and record it in a data table. So we call that event-based data collection. And to enable that, I click in this lower left-hand corner in this mode button, this data collection settings. It pulls up the data collection settings. This is where I changed the duration of my time run in the last experiment. I want to completely change the type of experiment. So from the mode drop-down menu up here, I will select event-based. And for the event name, I think I'm just going to call it sample, because we're going to be doing a couple different variables. So I'd rather just type in the field what I'm doing and say done. And so now it automatically brings up this table, so I can see as I keep the data, it's stored in the table. And then I do want the meter to be bigger. So again, I'm going to come into my box of boxes and turn on the big meter. And this pH probe is acting very funny. It's because it's laying down and it's not in its storage solution. So when I stand it up and it's in its storage solution, it should be reading about 3 or 4 pH, because the storage solution that it always should be stored in is a pH 4 buffer with some potassium chloride in it. And so I'm going to take it out of its storage solution and give it a good rinse. I do want to say that I am using today our flat pH sensor. If you have our kind of regular pH sensor, which has an exposed glass bulb at the end, you can use it for this experiment. When I'm working with food and anything that is not very water-based, liquid, very thin, I prefer to use this one. One, it's easier to clean, but two, it's actually designed to work with kind of chunkier, bigger foods, soil slurries, different things like that. It has a double junction in it, so it helps it from getting stuff stuck in the bulb and causing a lot of errors in your readings. So I prefer this one a lot. I'm going to go ahead and start data collection. Nothing is going to happen in event-based mode until I press the keep button. So first I am going to, let me see here. I'm just going to measure the pH of my whole milk solution. And I'm going to pour, let's see, about 40 milliliters into just a smaller beaker, so I don't have to use as much lemon juice. And I'm going to let that stabilize. And it looks like it's stabilized about 6.65 pH. I'm going to press keep. And I'm going to call this whole milk. And I'm going to keep. And now it's asking me, it's telling me basically, you didn't enter a number, so do you want to call this categorical data? Yes, I do. And now I have my data point for whole milk. Next, I want to make sure I rinse off my whole milk. Move this over here so everyone can kind of see what I'm doing. Okay, and now I'm going to pour oat milk into a second beaker and kind of watch it and see that, again, to look at the differences between the oat milk and the whole milk. And then I'm going to measure its pH. Wait for it to stabilize. And it's a little bit more basic, so 7.8 instead of 6.7. And 7.9. So I'm gonna call it there and keep. And this is oat milk. And keep. All right. And now for the exciting part. So what does everyone think is going to happen when I add acid to the whole milk? Is anything going to change physically or pH wise?
Well, if you're adding lemon juice, I guess I should let Dylan answer. Dylan's our student.
Yes, yes. So, okay, so Randy asks a good exploratory question, which is how much lemon juice are we adding?
I am not going to add very much at all, probably a milliliter to what in here is about 40 milliliters.
Okay. All right.
Maybe 1 to 2 milliliters.
So my guess, and it looks like my study group backs me up on this one, but if anyone thinks differently, let me know. I think that we are going to see a little coagulation, a little curdling. Let's see. In terms of the chemistry here, it looks like Julie suggests it's going to lower the pH.
All right.
So here's my question. I'm taking this now of like, which one will the pH go the lowest on? Is there any buffering capacity in either of these?
Oh,
I'm getting complicated
you
now.
are.
Sorry.
Let me make sure.
AP student.
Yeah, the AP student there. I'm going to get these a little closer in volume. Everyone's getting real technical as I have beakers. In vain, here I am. Okay. All right, so I am going to add, is this one of our 1 milliliter ones? It is. Okay, I'm going to add 2 milliliters of lemon juice to the whole milk. All right, hopefully everyone can kind of see.
We got some people thinking the oat milk's going to be more acidic and some that think it's the whole milk.
All right, so I added lemon juice. Get some close-ups here for y'all. I know, the close-up, the exciting part. All right, so this was the whole milk. All right. Not too much physical change, a little bit. You can kind of see a few little curds on my stir stick. So I'm going to do another 2 milliliters. So we'll end up having added 4 to 40. Now we're getting a little bit more on the sides coming in. And so you can kind of see it on the stir stick there. I also have, can you see at all?
I can move it in more.
I put it on behind my black. There we go. There's some little curdles. Can also see if my fork. There we go. The fork shows it pretty well. Get that back in there.
As someone said, yes, we're just making yogurt.
All right, and then the longer I let it mix, the thicker and thicker this is getting. All right, now let's measure the pH. And so people said the pH was going to go down, right?
Yes.
Okay. So let's put this in here. See, a really good reason why I use the flat pH probe.
Ooh.
Yeah. So 4 milliliters of lemon juice. Definitely going to lower that pH. Went pretty low there, down to 4.
That one a lot lower than I expected it to be.
Me too. All right, so this is whole. We're going to do plus lemon juice. Okay.
Mm.
And then now we're going to do the same thing to the oat milk. What does everyone think is going to happen?
Now, I saw this earlier. One of our attendees thinks that there will be, because oat milk has low protein, its curdle will be low. So for low amount of aggregation slash coagulation. So maybe still some curdling, but not very much. Oh, Mary suggests maybe we should take the pH of the lemon juice.
Oh, yeah, we probably should have.
I can go get
To
another beaker.
context, I have one here
Okay.
that I didn't use the way I thought it was, so I have an empty
Perfect.
one. I will do that after I'm done with the oat milk, but I think that's really good to give kids context. All right, so I'm going to add 4 milliliters of lemon juice to my oat milk and stir it, kind of treating it the same way I did with the whole milk. So that was 2 milliliters. Not really much going on there. Nothing really forming on it. So let's do 2 more. Not much going on. It's pretty smooth. Let me get my fork cleaned. Fork test. Very
Very scientific.
yes, very scientific, technical. But yeah, the more I mix with the whole milk, the more I mixed and got the acid to interact with the protein in the milk, the more it came out of solution. This one's really not doing that. If I pull it up with the fork, there's really nothing on
There
the
is
fork.
nothing.
So it's still very, very smooth. Now let's measure its pH. And look at that. It also dropped just like everyone thought it would, because we added an acid to it. But it is the same pH roughly as the whole milk. So you can have the same pH, but have very different physical reactions.
Joshua asked a good question. Can you add notes or qualitative data for each bar in your graph?
So what you can do, because we are in GA Pro.
To be over here?
No, it's,
Sorry.
yeah, that's right. Because we have GA Pro, we can add notes from our box of boxes. And this will allow us to, I think you can only add 2 at a time. Write notes about, so like sample 3 added 4 milliliters lemon juice, saw curdling. I don't know how to spell curdling. Saw curdling after mixing. And then you could say sample 4 added 4 milliliters lemon juice. No physical change after mixing. And the notes will save with the file and all that good stuff. So that is a nice feature of GA Pro. Let's go ahead and measure the pH of the lemon juice, just in case your students said maybe they thought the pH would go up with lemon juice, or you haven't really talked to them about acids and bases too much yet. But what would everyone expect the pH of lemon juice to be?
Dylan?
Oh gosh. I'm going to say two. Okay, my group
Would
said.
you, yeah, sure. Give a number or acidic or basic is probably sufficient in this case.
Okay, thank you. I was okay, perfect. Acidic.
High or low?
Low, low.
Low. Okay, down low. All right, we're expecting it to be low. Okay. And so now I just have my tiny meter down here. Yep, it's right about 2. So I'm going to press keep and I'm going to say lemon juice. So now students know why it went down when you added lemon juice. So very important part of that. I'm going to go ahead and stop data collection and so why did the pH, so if the pH of the final solution didn't change, why did one have such a dramatically different physical response than the other? Dylan, any guesses?
I mean, I still think it has to do with the proteins. Okay, Jen has given me a great word to use, which is protein denaturation.
Close. Denaturation.
Dang it.
Yeah, so the fact that we have changed the pH has changed proteins are by their nature, what makes them amazing is that they have a very stable charge. And when you adjust the pH, they're going to lose that charge balance and start falling apart and clump all up and clump with each other. So this is a great way to teach intermolecular forces and charge balance and interactions with hydrophobic and hydrophilic. If you're looking for any of those key terms, because intermolecular forces, I feel like is something that is so fundamental, but really hard to teach or make it like a very physical view.
Oh, yeah.
So I really like it for that.
Yeah, and I do agree. I think it is kind of more of the coagulation of the proteins together necessarily than the denaturing because because it is that heterogeneous solution. It's kind of pulling them out and clumping them together.
Yeah. Yeah, you're right. I mean, I still think there's probably some
there's probably some
but I think that's the predominant.
Some protein in there, I'm sure that's denaturing, but the major what we're seeing is that coagulation.
Yeah, but they can't do that unless they lost their charge.
Right, exactly. They still have to stick together. Yeah.
Yes.
I think Will got it right there. They denature and then stick together in new ways. Yes.
Yeah. So first one, then the other. But oat milk doesn't have that because it does not have as much protein. And you can see now that it's been sitting a while, it actually does have a little bit more.
And I forgot to bring
almost none.
Yeah, and I forgot to bring the bottles in so we could see the ingredients of them and the nutrition facts. And you could see
because he also got no sugar oat milk.
Yes.
So that was kind of another variable. And so this activity you could really see branching out and looking at the sugars, especially looking at temperature. Because if I warm up the milk, then I can put it in my coffee really easily without it falling apart, like talking about that and what all that means. So
yeah, and then we also have protein is the big thing now, and so many things have added protein to them that when I looked at the oat milk, this was just plain oat milk. It was not very much in it besides oats and a couple other chemicals for stabilizing. And the protein level in it was only 1 gram per serving.
Yeah. And
compared to whole milk, it's a lot more.
Stabilizers and fats. And so that is kind of what is more predominant in the plant-based milks versus protein.
Yep.
So that is why the whole milk does it really quickly and grossly. And the oat milk is like maybe there's a couple little ones on the side there.
Yeah, and as someone said in chat, the calcium carbonate, I remember that calcium carbonate being on the list of ingredients as a stabilizer. So that's why it's going to be a little more basic.
Yeah. All right. Well, on to the I can
Oh,
move it if
okay.
you want
All right.
while you set up. And next, we're going to move on to pigments in foods.
So I'm hopefully not going to make everybody dizzy here and
Close your eyes
move
briefly while we move the camera.
camera to my colorful collection.
Ooh.
So one of the things I always love looking at the different types of pigments that we have in foods. And one thing that I always like has stuck with me when you're, trying to eat healthy, everyone always says, eat the rainbow, eat as many different colored, basically vegetables and fruit and things that you can. And there's a lot of questions of like, why? Why should we eat all this colorful stuff? Well, there's kind of two ways to look at it. From a chemistry way, you have that color is actually the evidence of molecular structures in there, that we're looking at very specific pigments that are present in the different plants that we're looking at. And on a more biology type side looking at it, we're looking at it more that each color is actually representing a very specific pigment and kind of different forms of these pigments. And the idea with these different pigments is that they also are contributing to specific nutrients and antioxidants to help us get a much more balanced nutritional diet and to make sure that we have a complete meal and complete nutrition. So we're a little short on time, so I just wanted a quick show of what we've done here. So basically, I went and bought an orange and I extracted from the orange peel and then orange juice itself. We have Swiss chard, kale, carrots, and yams or sweet potatoes, if you will. And I just want to quick show how I did these extractions because it's one of those we do get asked this a fair amount of how we can do that. So in some cases, if it's a really soft leafy green, you can usually not have to use a mortar and pestle. But with kale and sweet potato and carrots, they're a little more, they're a lot more robust. And so having something like a mortar and pestle is really useful to help do that extraction. So I basically just took some kale and, you know, tear it up here, and then I'm going to add some isopropyl alcohol. This specifically is 91%. That is just bought from a drugstore, grocery store, and I'm very precise. I just add some. And then what I want to do is kind of get some agitation here because the idea is that by using the mortar and pestle, I'm helping break down those cell walls. So I'm breaking open the cells so that I can extract these pigments. So we're actually taking the pigments out of the cellular structure and we're not changing the actual molecules themselves. We're just trying to isolate these. And just a little bit like that. And then I take the very fancy filter here of coffee filter. And I'm going to make a little funnel from it. Do you have a clean beaker? That works.
Yeah, let me rinse this lemon juice residue. There you go.
So I'm gonna do that. Put my beaker under it, and then I'm just gonna pour my delightful green fluid right in here. And the reason I have a coffee filter there is I want to make sure I get the particulates filtered out because those can cause some interference when I'm trying to actually get a spectrum of them. So that is how we do our extraction. And I'm just going to quick do a sample of data collection here. So instead of graphical analysis, we're going to use our other app, Spectral Analysis, and this allows us to use our spectrophotometers. So I have our spectrophotometer here. I have turned it on, and we're going to connect it just like we connected our probes in the other app by Bluetooth here. And so as it's connecting, it is going to have to warm up for a period of time because it does have an LED lamp in there that does need to warm up a little bit. And we want to just look at our wavelengths of these because I think this is one of the coolest things, especially for talking with biology, is talking about the spectrum, that a lot of times students just get to see a spectrum on a graph in a textbook. Rarely do they actually get to do it themselves. Or, when we were students, you have the huge Spec 20s and they took up the entire lab bench practically. And so now using something like this is super simple, and we can go ahead and do a comparison and look at what wavelengths are being present with these different pigments and if they're all identical or not. So I'm going to do, as it warms up, I'm going to prepare a blank. So I'm taking some of my isopropyl alcohol here and putting it in an empty cuvette. I want to make sure, okay, it's nice and clean. We're going to still keep warming up here because we want to make sure we get a good spectrum. And while that's warming up, I'm going to go ahead and prep my other samples here. So I have some of my kale juice, if you will, that I extracted earlier. And that's the other thing, I extracted it and then let it sit. So some more of the particulates would filter out or settle down, I should say. That's the kale. I'm going to do some chard. So this is Swiss chard, which I'm very interested in seeing how this is going to appear. Because if we look at the Swiss chard here, it came out as this lovely brown color. And when you look at the plant itself, it's kind of this green and red, and it's really pretty. And yes, we know comfort foods. In Oregon, kale is a comfort food. Okay, so now that we've fully warmed up, we're going to finish our calibration. I have my blank in there. We are going to calibrate, calibrate, going to calibrate, calibrate. All right, I'm going to take my blank out, and we're going to do the kale first because those of us that are biology people know exactly what this one's going to look like. Yay, chlorophyll. Oh, look at that beauty. Wow, that's really pretty.
That's really pretty. It's
a little saturated. Yeah.
Dilute it if we had more time.
Mm-hmm.
The reason I would want to dilute this is because it's way above an absorbance of 1, and you lose a lot of accuracy in that zone. But we're looking at the shape, and yeah, if you're familiar with the spectrum, it looks really good.
But why don't I have a peak in the green when it looks green? Dylan?
Dylan?
Yes, I can weigh in. All right, I believe it has been explained to me that we are looking at what is being absorbed by the light. And because there is so much green in the solution, that's not getting through or it's not being absorbed. I don't know. Help me in the chat, you guys.
All right. Now, this is the one I'm excited. I did not do this one before because I was really wanting this to be a surprise for all of us. So this is our Swiss chard. What do we think it's going to look like?
Too concentrated, what I'm guessing.
Oh, also very concentrated.
Very concentrated, but it has more in the green here that doesn't look like it's just more.
Here, I'm going to take out some and add more. I'm going to add some. IPA to it.
All right, and because we're gonna have a lot of samples, I'm gonna start renaming some of these. And again, if you want to change something, you click on it. So I named the data set one kale. All right, what's this one?
This is chard.
Chard. All right.
Ooh, still pretty concentrated.
Still pretty concentrated, but we can tell at least there's something right there.
Yep. It's
So
definitely a
rename
little bit more kind of yellowish color to it. All right, let's do some carrot. This will be next.
Yeah. Oh, and this one's what color to the eyes there?
Yeah, this one is a little more on that yellow spectrum here.
So that if your eye is seeing yellow, I see a lot of people trying to help out Dylan. If your eye is seeing yellow, then that means the opposite color will be absorbed.
The premise of the color wheel.
Yes, and so that, wait, oh, sorry, let me press stop. And that is accurate here because the opposite of yellow is blue, and we got a nice big absorbance peak in the blue.
Now let's see, I'm going to do yam next. Let's see here, does the yam and the carrot, so we have
both kind of yellow.
Yam and carrot are both very yellow. Are they going to have the same pigments in them? Oh, interesting. Looks like they do.
They're pretty similar. They're a little bit shifted.
Little bit, yeah.
This one looks a little bit higher. And then, of course, this is a visible only spectrometer. So it might be kind of fun to see kind of what's on the tail end of the UV here. If we got more characters in, but
I don't think we have time for the orange.
We don't have, we're all out of time. Let's see. What else do you want to say about these?
Where's my cheat sheet slides?
Oh, okay.
All right. So just a couple things to also think about here is that in plants, the pigments actually have function, they influence the function and survival. So obviously we'll talk chlorophyll is going to be the most obvious one of these because it's going to be used for photosynthesis, so plants can actually make their own food. While for consumers, and I say consumers in general because it's not just people, it's other organisms that eat plants as well, these pigments are corresponding more to nutrients and antioxidants. Also, why use spectroscopy? One, it helps explain this idea of when you see something and you're seeing that color reflect back to you, that's the color you're seeing. That's not what's being absorbed and used. So by using the spectrophotometer, you're actually able to see what wavelengths are actually being used with those different types of pigments. Obviously, for chlorophyll, for example, red and blue are our primary colors that we look at. And if you look at a grow light, that's the type of light that is used in grow lights. The other thing something that we kind of looked into a little bit, and we didn't get to explore it too much, but it's also really interesting to see that foods can change color when they're cooked or processed. And that also has to do kind of a combination of these pigments and molecular changes that can happen to them. For example, if you've ever used cabbage as your pH indicators, or when you pickle cabbage, it kind of changes as you go. So there's a lot of really interesting things there. So we're going to jump right into the end here.
Yeah. Sorry, we ran a couple minutes over, and all these people are very patient, and they may want to win a temperature probe.
Absolutely. Thank you. So as we've been sitting here and between me answering questions about science, I went ahead and entered everyone's name into a random name generator to see who's going to win a Go Direct temperature probe, which you can do a few of today's experiments with today. The winner is Will W. So congratulations, Will.
Yay, Will.
Yay, Will.
Will, I'm going to email you to get some information about where to send that Go Direct temperature probe. So keep an eye out for an email from me. You should be getting it here in about 10 minutes or less. And thank you all for joining us. It looks like there we go. Yep. Thank you all for joining us. We will be back for another webinar on Thursday. I dropped a link to get some feedback from you all in the chat and would love to hear from you about what you thought about today, if there's anything you want to learn about, any of that good stuff. Anything I missed, Colleen and Melissa?
No, thank you all for coming out and letting us amuse you with our entertainment of having some fun here with comfort foods. And I dropped a copy of the slide deck into the folder that Dylan had shared that has the certificate as well. So feel free to use it as you need and ask us any questions. You can reach us by email very easily.
Yep.
Or chat. Or phone.
Or phone.
All of the above.
Whatever you want.
Mhm.
All right, everyone. Have a great rest of your day, and thanks again for joining us.
Bye.
Bye, everybody. Thank you.